Hello friends, in this video we are going to learn last property of Laplace transform. That property is known as Laplace of derivative. So let us see what is the property. Just like Laplace of integration, this is Laplace of derivative. Dash means derivative. So traditional notation for derivative. Left hand side is easy. Right hand side contains two terms, s into phi s and then f of 0. So first of all we prove and then we conclude by taking one example. Ellipsis. Laplace of derivative. Which is same as integration of infinity for minus st into f dash of t dt. It's a usual thing, okay? It's a formula for Laplace. Then we integrate by parts again. Integrate by parts because it's a product, okay? Now we call it as u and we call it as v or suitable. Derivative and integration will cut and we are comfortable. Therefore, we have chosen this to be u and this to be v. What is integration by parts? U into v is equal to u integration v minus this. Fine. It's written in short. Okay. So this can be continued u as it is. That means series to minus ft as it is. Right? And derivative f dash v. That is integration of v. So integration of f dash v dt. Right? Then here we complete this 0 to infinity, then minus this we write 0 to infinity. Inside the bracket, this integration remains. Integration of f dash of t into dt, and then u dash. U dash means derivative e, and it is there minus s raised to minus st into dt. What happens if we put up infinity? See this picture here, e raised to minus infinity. This is equal to 1 upon e raised to infinity. But e raised to infinity is infinity, and 1 upon infinity is 0. That's why this comes 0. But what happens if we put t is equal to infinity here? Before putting, we have to complete one step. This integration and derivative get cancelled. Integration and derivative get cancelled. It's a basic result. Integration of f dash comes f, and therefore this is f of t. Then we put 0 to infinity. This minus and this minus becomes plus. Yes, we can take outside because it's a constant. 0 to infinity. This story we have seen. Dash and integration cut, and we are getting f of t simply. It is there. E raised to minus ft into dt. Now we put upper limit, so that comes 0, and if we put 0, then we are getting f of 0 because e raised to 0 is 1. Okay, this is simple. So 1 into f of 0, it remains plus yes as it is, and this whole thing is imagined to be Laplace of f, right? And this comes yes into this is denoted by phi s, and this minus f of 0 is later. Full stop. This is what is the proof. It's very simple and interesting, right? So remember, integration by parts is useful for proving these properties. Now we conclude with the help of one example. Examples are tricky, okay? Maybe for 1 mark, maybe for 5 marks, okay? So let us see example. If f of 0 is equal to say 4 with Laplace of f of t is equal to 1 s divided by s square minus s plus 3. Then find Laplace of f dash. See the method of asking question. You are not given f of t. This is what is the trick. And we don't require f of t. Directly we can find out Laplace of derivative. Solution. Laplace of derivative, just now we have seen s times phi s minus f of 0. Now we have to find out phi s, that's all. So phi s is also given. Here phi s is nothing but Laplace of f of t. See this notation. And which can be written as that given value directly, s square minus s plus 3. Also you are given this value which is useful for finding Laplace transform. This f of 0 is 4. How? We don't know. It is given. So number this property as 1. And mechanically we can put this in 1. So Laplace of the derivative f dash, f we don't know. We are asked that. Therefore keep as it is and follow this property. S times s is compulsory. Phi s is also there. Yes, divided by s square minus s plus 3. Bracket complete. And then minus f of 0, that is minus 4. S into s becomes s square. Not necessary to write this also. Direct answer. That's all. Thank you.